Orbital diagrams are similar to electron configurations, but they give us a little bit more information about the actual structure and the ordering of the electrons, and it's important to know a couple of rules when you do orbital diagrams. Let's do something simple first, which will be beryllium. Beryllium, being the fourth element, has 4 electrons total when neutral. The way that you would do them, according to the Aufbau principle, is to start at the bottom, and then arrows represent the spin of an electron. Electrons can be single, or they can be paired. And when they are paired, they have opposite spins, and those spins are denoted by an up or a down arrow, either a whole arrow or a half arrow. If I were to stop right now, I would have 1s with 2 electrons that are paired in that sublevel. That would represent helium. I know I have 4 electrons I need to diagram, so that would be going up one more level, up and then down. There are 4 arrows, which represent 4 electrons in beryllium. The electron configuration for beryllium in full would be 1s2, 2s2. If I needed to abbreviate this, then I would use helium, which is 1s2. So the abbreviated form for beryllium would be helium in brackets, and then whatever was not contained in helium, which is 2s2. The Pauli exclusion principle gives us some guidelines on how we fill these orbitals up. First of all, you cannot have both 2 ups or 2 downs. Also, a maximum of 2 electrons can go in that particular orbital. So 3 is out of the question, and so is every number above that, of course. And then conventionally, up goes before down. That is the Pauli exclusion principle, but sometimes you will see abbreviated as PEP or PEP. Now we're going to do the orbital diagram for carbon. We're going to start off with the electron configuration for carbon so you can see how the orbital diagram gives you a little bit more information. The electron configuration for carbon in full would be 1s2, 2s2, 2p2. To see what's happening inside as far as the orbital diagram goes, it would look like this. 1s2 has 1 up and 1 down, and I'm starting of course there because of the Aufbau principle. 2s has 2 electrons in it, up and down, and now we're going to look at the 2p level. 2p has 2 electrons, but how are they arranged? Some people may think they're arranged like this, but that would be incorrect. The electrons are arranged in a way that, according to Hund's rule, says the electrons will spread out amongst the 3 different sublevels, orbitals in that level before they double up. So those 2 electrons in the 2p are going to be up and up. They won't be next to each other because you can think of this as strangers getting on a bus. If strangers are getting on a bus and there are empty seats available, people tend to spread out before they have to sit next to a stranger. And the same thing applies to this bus. And this bus has 1, 2, 3 different seats available, and it can hold a maximum of 6 people, so to speak. But those 2 people on the bus are not going to sit next to each other unless they have to. So when the 4th person gets on the bus, they have to sit with the 1st person. And that'll make more sense if we do something with a higher atomic number. Nitrogen's electron configuration is 1s2, 2s2, 2p3. Starting at the bottom, we do up, down, and then up, up, up. This gives you the increased level of detail, this orbital diagram, because if you were asked to describe the highest p level, as far as the electron structure of it, you would be like there are 3 unpaired electrons, and there are no paired electrons. That is not easy to see from just the configuration itself. The orbital diagram for oxygen will start at the bottom as expected, up, down for the 1s2, up, down for the 2s2, And then the 2p4 will be up, up, up. But since you've run out of individual spaces available, you have to go back and then double for that very last one, which will be down. That gives us an electron configuration of 1s2, 2s2, 2p4. Now let's talk about valence electrons briefly. Valence electrons are the electrons in the highest energy level. The highest principal quantum number in this case is a 2. And we're looking at the s and the p. That would represent this level here. The sum of 2 and 4 is 6, which means that oxygen has 6 valence electrons. The easiest thing to do is to find the highest s and p in that order with the same large integer, which is 2, and then take the sum of their superscripts. Or you could just find oxygen on the periodic table and see that it is in the 6th tall column. Now we're going to do iron. Let's do the full electron configuration for iron, and then we'll do the abbreviated electron configuration for iron, and then do the orbital diagram for iron. So iron, which is Fe, the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then remember that D starts with 3, 3d6. The electron configuration for argon is 1s2 all the way through to 3p6. So the abbreviated form will be AR in brackets, and then everything that does not fit inside after it, which would be 4s2, 3d6. The orbital diagram for the Aufbau principle says to start at the bottom, up, down, and then we continue 2s. 2p will be filled in with 3 ups before you do the 3 downs. But since we're going all the way through and filling in the entire 2p level, then there's no, on paper you can't tell what order someone did it in. Just make sure that you do it correctly, because sometimes when you stop in the middle of 2p or 3d or some other p or d orbital, it is important to make sure that Hund's rule was satisfied. And as you see, we're still going to fill up 3p, because it's going to be 3p6, 4s2, and then go over to 3d and put in 6. It'll be 5 ups, and then 1 down, giving you a total of 6 electrons in the 3d, with only 1 pair of electrons, and then 4 single electrons. That would be how you would describe the 3d level of iron.